Okay, so this talk is about, of course, joint radar sensing and communication, and the title is a little bit provocative, and say joint benefits for free. Let's see. First, I would like to also to acknowledge my collaborators, in particular Mari Kobayashi from Supelec Technical University of Munich, Gerhard Kramer, Technical University of Munich, Giulio Colavolpe from University of Parma, Lorenzo Gaudio from Parma, and then Said Khalil De Cordi and Fernando Pedraza Nieto from the Technical University of Berlin. Okay, the context, I think by now we are familiar with the context because it was also widely discussed in the previous presentation in this webinar series. So the idea is that wireless networks transmit a lot of radio waveforms and a lot of energy that can be somehow exploited also for sensing information. And here I will mainly focus on communication aided by sensing rather than vice versa. In a sense that, well, sensing with communication waveforms is expensive. So it's not really for free, but the expenditure, we will see, comes in terms of complexity. Because of course, sensing is like a typical radar waveforms are also designed to enable low complexity detection schemes. While OFDM or TFS, whatever digital modulation waveform is designed to carry information, and therefore extracting sensing information is typically much more expensive. However, it comes for free in the sense that it does not use more bandwidth or more transmit power. The waveform is there anyway to carry data, and so it's transmitted anyway. There is no added expenditure in terms of power bandwidth. So, okay, so this is basically more or less what I want to say. So before starting, I'd like to somehow review a very simple information theoretic toy model, which actually somehow shows two things. First of all, that doing things jointly rather than sharing resources in a, let's say, orthogonal way, like putting these two systems on different time slots or bandwidth, is extremely convenient. It gives much better performances. And also that there is very, very little to give up in terms of information rate while achieving almost ideal sensing. So the model is simply a memoryless channel that depends on a state. So the input of the channel is X, the output of the channel is Y, but there is also a state S, that is a state here in the conditioning, and another output that can be seen as a generalized feedback. Typically, they say Shannon feedback will bring back the output to here, right? But this is a generalized feedback. This variable Z, at time I-1, is brought back by the channel. In a certain sense, this represents the backscatter channel that comes back to the transmitter. So, of course, the goal is to communicate information. So there is an information message here that has to be transferred to the receiver. The receiver has ideally perfect channel state information, so it knows the transmitter is to estimate the state of the channel. So the estimator, knowing what is transmitting, and from this generalized feedback, wants to come up with an estimate of the state of the state sequence. So, of course, this channel model is very simple because we already know that memory feedback does not increase the capacity of memoryless channels. So the feedback here plays only a role of enabling the estimation of the state, but does not really make change radically the transmission strategy. Of course, the model could be made more complicated by introducing a channel with memory and generalized feedback, but of course, this would be a much more difficult model. So in this case, the goal is, of course, to communicate information reliably. So with the probability of error in the limit for large block goes to 0, and estimate. So for a given distortion metric, so classical additive distortion metric, estimate the state such that the average distortion over the sequence of states is less than some target D. And we can study the capacity distortion function for this channel, which is the supremum of all rates R that are achievable subject to this constraint on D. And it is not difficult to show that the model here, I mean, the result is that the capacity distortion function is the maximum of this conditional mutual information, where the maximum is obtained over all input distributions satisfying the distortion constraint on the state. So in other words, one has to come up with an estimation variable and a probability distribution that maps X and Z into S hat, and of course the distribution of X such that this mutual information is maximized. In addition, one can also easily show that the mapping of XZ onto S hat can be restricted to be a deterministic mapping. So although here we take this maximum of all possible distributions of the S hat given XZ, as a matter of fact, a deterministic function that maps input X and feedback Z into the estimated state is enough to exhaust this maximum. So if we particularize this simple channel to a Gaussian channel with fading, of course here everything is IID because the channel is memoryless. Well, the Gaussian, the scale Gaussian channel with fading is represented by this. So at time I, we receive a scale version of X plus noise, and the state is multiplicative with respect to the signal. And we have an input power constraint. In addition, we consider the quadratic distortion function. And it turns out that we have already some interesting thing. If we use a signal X, this is a real model, so constant envelope, so basically just plus and minus 1, so like a 2 PAM signal. When our rate is limited at most to 1 bit, in general will be less than 1 bit per symbol, but the distortion is minimum. Is minimum because we see that this is a convex function, and therefore, for all signals X, all distributions with a given variance, this is minimized when X is constant. So magnitude of X is constant. So the 2 PAM is optimal for distortion. On the other hand, if we make X Gaussian, of course we achieve the capacity of this channel, but the distortion will be what it will be. And one can plot this, for example, and see that this distortion in the state estimate capacity or achievable rate of the channel is this red curve. Now, there are two considerations here to do. The first consideration is, well, this point is achieved by BPSK, this point is achieved by Gaussian inputs, but in fact, we notice that, interestingly, actually, this point is already at the maximum capacity, and the degradation in terms of estimation is very small. Or vice versa, well, this is the minimum possible distortion, and the degradation in terms of rate is not that great. So this is what I say achieving, benefit for free. This curve, well, if it was just one single point here that dominates all the curve, then we would have at the same time maximum rate and minimum capacity. It's not quite that, but it's very pointy. There is very little trade-off. In contrast, if we would share resources and put the radar and the communication on, say, orthogonal symbols or orthogonal bandwidth, we would move along this blue curve. And now you see that there is an enormous gap here. So this suggests two things: doing things jointly is better, and also there is not much to give up in terms of communication when you want to also estimate the state. Now, it turns out that for intuitively, and this is what I'm saying is an intuitive statement, if the channel has memory, then this generalized feedback can increase the capacity of the channel with respect to the case without feedback, which means it's not only achieving the capacity of the channel itself or approaching that capacity with a good estimation error, but the fact that we can sense the environment can actually improve the communication. And this, of course, is a very interesting challenge, is to look at this problem in the case of channel with memory, because one may imagine, so now what is a channel with memory? Okay, well, if the fading has memory, no biggies. Is yes, you gain a fraction of a bit. Is not very interesting. I mean, is interesting from a theoretical viewpoint. One has to work very hard to get nice results. But the reward in terms of actual gains are not that dramatic. However, there are plenty of configuration, plenty of scenarios where the state of the channel is much more complicated and the memory is very important. For example, as I'm going to talk in a moment, the problem of beamforming in say millimeter wave communication. So you may say that the state of the channel is the position of the receiver, and the position of the receiver is not changing very quickly over time. So it is a state with a lot of memory, and communicating at millimeter waves and pointing a beam in the right direction makes a whole difference. Makes difference in terms of gain. Which means that if one can leverage the sensing information to improve the beam pointing, one can get many bits per second per hertz of improvement. Okay, so this is just a very intuitive and informal consideration that points out that for other models, for models that are clearly more complicated and more difficult to treat from an information theoretic viewpoint, and in particular models with memory, as in the motion dynamics of users, blocking probabilities, blocking events, and all these things, especially I would say related to millimeter waves communication, where pointing beams is extremely important, fighting against the free space isotropic propagation loss is one of the fundamental issues. there is a lot of potential to incorporate sensing information to help communication and actually dramatically boost communication. So in this line of thoughts, now I putting away my information theorist hat, and I look more at so we look at the problem of a base station, typically operating at high frequency millimeter waves, so typically non-isotropic, where propagation is directional and fighting against the path loss is very important, and therefore you need the beamforming gain. And then we may consider two typical scenarios. In the first scenarios depicted in this cartoonish figure here, we have unknown targets. For example, vehicles. Vehicles have a great advantage with respect to mobile phones. They are big metal objects, so their reflection is pretty good. The base station would like to, of course, identify them, so detect them, and extract information from the backscatter waveform in order, for example, to speed up the initial beam acquisition, also basically building side information for speeding up the beam alignment procedure. So the main problem here is target detection. And also we may imagine that, well, the base station is not yet communicating to this unknown target. By definition, they are not yet connected, they are unknown. So it does not even know if they are there. So we may imagine that the base station is illuminating a certain angular sector with a wide angle beam like this, which may correspond to a control channel. So we may have, a broadcast downlink control channel, for example, broadcasting common information to all the users. So here there are, in fact, other users, imagine other users that are already connected, and the base station is just sending its presence in this area, but at the same time, there will be backscatter wave for backscatter signals from these unknown targets. Of course, the base station already know the known targets, so it can already use some side information there to do the radar detection, and this is when communication helps radar. This is not a typical radar problem where the radar is completely blind. The base station knows a lot of things about its environment, knows already all the targets it's already communicating to, they're already connected, the base station knows, is pointing beam at them, knows more or less their angular position, so there are a lot of information that can be used in extracting the parameters, so detecting the unknown target and extracting and estimating the parameters. Then we have a second scenario where the base station is already communicating with known targets, so is already pointing independent data streams at those targets. They're beamformed independent data streams. But nevertheless, the base station wants to extract, so estimate parameters, for example, velocity, range, and angle of arrival, because communication is already taking place. Those parameters may serve to help beam tracking and refinement. So that's conceptually different from the first scenario. In the first scenario, the main problem is target detection. The question is a hypothesis testing: is a target there or not, or are there multiple targets? If it is a multiple target detection problem, here there is no detection problem. So I'm getting very nervous when people who are, of course, very proficient in radar say, okay, but where is the problem? Is detection? No, when the base station is already communicating to somebody, already knows that somebody's there. So there is not a detection problem anymore. This is only a problem of parameter estimation. Okay. And of course, it's a bit different because when the base station knows that the target are there and is already communicating with them, is actually illuminating them with individual data streams that are already being formed to the target. So of course, the signal to noise ratio, operating signal to noise ratio in this case is much higher than in this case because there is, isotropic. Or not really isotropic, but a wide angle. So here we, in a previous work, we have considered like a subcase that can be actually applied to both scenario 1 and scenario 2. This is the case where the base station is using, or it could be a base station, could be another car, but is already using basically a relatively narrow angle beam. So it could be the case where you're using beam scanning, and at this point, if in practice, one would use these rotating antennas if it is like a military radar or a avionic radar. But of course, normally in this case, one would use a phased array. But one can point a beam and move it at given angles. So apart from the discretization of this beam scanning scheme, there is no angle of arrival problem here. The only problem is target detection. So is there a target in this beam or not? And the parameter estimation. So in this case, we have looked at the case of parameter estimation. So the case where the base station is already communicating to a user in that direction is a sort of like preliminary approach, and the channel model of the backscatter signal is classical multipath channel model, where every path contains a delay and a Doppler shift and a coefficient. So discrete multipath is frequency and time selective because you also have Doppler frequency shifts. And we have considered both OFDM modulation and OTFS modulation. In particular, so they are both linear modulation. So formally, the whole structure of the transmitter and receiver and the radar parameter estimation, when it is posed in terms of maximum likelihood, is very similar, because the only difference is, well, the data will what happens? Data will somehow appear as linearly in the received signal. What changes is how the parameters of interest. So in this case, the path coefficients, Doppler and delay, will appear inside the received signal. And one can work out some math, and at the end, not surprisingly, one can find at the end these type of expressions where everything, well, the coefficients and the data are always multiplicative because it's a linear modulation and the channel is a linear system, so no big surprises. And the expression of these blocks depend on the delay and Doppler, and this, of course, is modulation dependent. But this is absolutely not surprising. What happens is that one can write a joint parameter estimation, estimating the 3 times p parameters of these problems. You have p multipaths, and then each path component has 3 parameters. Of course, a simultaneous maximization of the likelihood function or the log likelihood function is very heavy. So what we do, we can do like a discretized search and iterative by solving for one coefficient and then replacing back. So it is essentially a generalized likelihood ratio test, as we say. Well, one can also work out the Kammerau bound. Again, that's a general story for signals in Gaussian noise. It's the form is always the same, and look at the performances of we chose as other works. We chose AO2.11p like parameters, not exact, but somehow the ranges, transmit power, frequencies, bandwidth is fairly comparable. And what we see in this case is that so this is, for example, is velocity and range estimation. So this is the root mean square error for velocity and root mean square error for the range, or therefore for the main path, assuming, of course, line of sight of the main path. And we see that both for OTFS and OFDM, the curves, these errors collapse on the Kammerau bound and follow the Kammerau bound over a fairly large range of signal to noise ratios. This is a signal to noise ratio at the radar receiver without where the beam forming gain is already taken into account into the computation of this signal to noise ratio, because we are assuming to point a beam and both at the receiver and the transmitter. At the transmitter and the receiver, the radar receiver. Interestingly, when we compare with the performances with the radarly optimized or designed waveforms, like, for example, the FMCW, which is essentially the chirp, we see that the performances are identical. And this is absolutely not surprising, because for the same duration and bandwidth, the fundamentals are there. Is actually digitally modulated signals for a given duration and bandwidth are fantastic radar waveforms. They have a fantastically good ambiguity function, because they are essentially like very similar to white noise. So the problem is, of course, the complexity of the receiver, because when you have a chirp, you can have a very simple receiver and extract the same performances with much less complexity. For example, to one for all, you can do it very easily full duplex, because the frequency of the transmitter and the receiver are always different because of the chirp. But when you transmit over the whole bandwidth, then you need either two co-located by fairly far apart transmitter and receiver, or you need some full duplex hardware in your transmitter. And in fact, I think that if I'm not a big believer in full duplex in general, I think that in terms of capacity, network capacity overall is not a good solution. But if there is one application for full duplex, I think it's this one. If I was people investing in full duplex or putting my emphasis on full duplex, I would say this joint radar and communication is one case where having a full duplex transmitter receiver at the base station side is really useful. Okay. So we can see presence of multipath leads to some little degradation, but not that much. So so basically, these are very encouraging results that pushes us to look at generalization of the problem. And the generalization of the problem is what we do now if instead of just pointing a beam in a given direction, we actually want to explore a wider angle and therefore also extracting, so first of all, detecting unknown targets and extracting also angle of arrival information. And so in angle of arrival information, there is an interesting thing here, is well, array processing has been there for forever, and we know exactly how to do angle of arrival with array processing, even at high frequencies. It's perfectly done, but it is done with waveforms that are essentially narrowband. For example, the chirp. And if the waveform is a narrowband, then we can sample every antenna, we can demodulate and sample. We can have a fully digital array processing, and this has been done more or less forever. With communication waveform at millimeter waves, well, the bandwidth of the signal is very large, and we know that sampling these signals, sampling every antenna and going to baseband is very expensive. So if we have 1 gigahertz of bandwidth and you have 64 antennas and you want to sample them, so demodulate and sample or direct RF, whatever you want to do, is a lot of bit per second. And basically this becomes incompatible with the power consumption of these front ends, especially if it is an integrated hardware. For example, the heat, this would melt, your chip very, very easily. So, and of course, people talk about even larger arrays, so 64, but it could be like hundreds. So a popular approach for millimeter waves, of course, is the hybrid digital analog beamforming, where we concatenate a digital baseband processor with a limited number of RF chains with let's say, configurable beamforming array that works in the RF domain. So the problem with this architecture in terms of radar detection is that we have a very large dimensionality reduction. For example, here we may have 8 RF chains, and here maybe we have, I don't know, 128 antennas. So this is sort of this dimensionality funnel means that we simply cannot directly sample all these antennas. We have to somehow project from dimension 128 to dimension 8 and sample this dimension 8. So this is an ideal scenario for, let's say, what is it? Very broadly speaking, compressed sensing. This is a paramount example of compressed sensing. Of course, the way the problem has been posed mathematically, the traditional compressed sensing is all discrete, etc., etc. Here we are looking at more like a super resolution if we talk about angle of arrivals and delay and Doppler in the continuous domain. So it is like a off-the-grid compressed sensing problem, but it is fundamentally a compressed sensing problem. So what we can do here is to design these sensing matrix, because this transformation, this projection from the antenna domain to the say RF chain domain or beam domain, some people call it the beam space representation, is indeed a projection, is exactly what the sensing matrix in compressed sensing does. So the challenge is to design this beam, this sensing matrix, and you know, what we want to do intuitively is to provide a good sampling of the angle domain, right? Sampling the angle domain, because what we want to estimate typically is quite sparse. So there will be a few directional arrivals. Let's say the line of sight path of the backscattered channel from signal from the targets, and so we have a fairly sparse signal in the angle domain. And we know that if we want to estimate something that is sparse in one domain, we have to do essentially random sampling, so random projection, and look at the dual domain. And dual domain will be, of course, the beam space domain. But random projections means also that using, for example, a roster of beams like in this figure is not a very good idea, because this would be, you know, regular sampling in the angle domain. You never want to sample uniformly and regularly something in the same domain in which that something that you want to estimate is sparse. You want to take random projections. So most likely one would design, you know, a set of beamforming patterns that will have some strange shapes, right? And then in order to trade off the ability of exploring the angle domain with the ability of having some beamforming gain in some directions. So this is an interesting open problem that we have not really solved, also because we know that from the theory of compressed sensing that the design of deterministic sensing matrices is one of the most difficult problems in compressed sensing. Almost all the results are stated for ensemble random matrices, and they hold with overwhelming high probability. So, for example, using pseudo-random beamforming patterns with some criteria may be a good idea. Anyway, assuming that we can do this, the channel model now is a little bit different, because now we have a signal that is transmitted. So in the case of, say, scenario one, when we transmit just one wide-angle beacon, well, there is only one data stream, and then this F, which is the transmitter, is just one column. If we are sending beamform data streams in scenario two, then F will be several columns, so one beamforming column for each data stream. And then we have these projection matrices here, which operate this dimensionality reduction from this is the steering vector of the array in direction phi p, and this matrix operates this dimensionality reduction from the antenna domain to the beam space domain. Anyway, what we obtain is a vector observation, and then of course we can do whatever we want. For example, we can do maximum likelihood detection, and now we have 4 p parameters. If we have p targets, we have 4 parameters. So the compressed amplitude, the angle of arrival, the Doppler, and the delay for each parameter. So we have done this. Of course, this becomes an interesting problem because the maximization of the likelihood function in this case becomes even more complicated. In addition, there are is an unknown number of targets. So you also want to do target detection, and so we have developed a coarse search, then some refinement, super resolution refinement, and some also successive interference cancellation to prevent, the shadowing of one target against another. And so, for example, these are results where we consider, in this case, this is the detection of a single target, and depending on the width of the transmit beam, we see that the detection probability collapses after a certain distance, and this depends, of course, on the beamforming gain, because the transmit power is always the same, but the beamforming gain is different. And then we have, velocity and range and angle of arrival estimated, conditioning on detecting the target, and of course, so in the range where the probability of detection is relatively large, and we can see that these follow the corresponding Kramer-Rao bounds very, very closely. This is also for OTFS modulation. This is another experiment where we consider one target that is fixed, and we move another target in a relatively narrow angle. So moving this other target, of course, as this is the second target becomes farther and farther apart, the risk is going to be obscured and obstructed by the fixed target, which is very close. So here we look at, for example, the target detection probability for the second target, which is this curve, and compared with the case where there is a single target, which is the previous curve for the same beam width. And we see that up to a certain point, up to a certain distance. So in this case, this car here is at 10 meters, so it's very close. And we start basically, we can detect the other, and the width here is 10 degrees. So we have a relatively narrow angle, and we can detect the second target up to 90-meter distance. The probability of detection of the second target is close to 1. And this is thanks to the successive interference cancellation feature of this detector, because otherwise this would be completely obstructed by the first target. For the second scenario, this is just a reminder of what the second scenario is. So we have individual beamformed streams. So of course, in this case, we are only interested in parameter estimation, because we already know that the targets are there. And we see that all the estimators, in particular range and velocity, they have this typical waterfall behavior. So they follow the Kramer-Rao bound up to a certain point, and then when the distance is too much, so the signal translation is not enough, we have this transition, so the waterfall transition, where the estimator deviates significantly from the Kramer-Rao bound. There is a little bit of an exception in angle estimation, because, of course, because of the fact that these are already being formed, so there is already some a priori information on the angle, which means that the angle error will never be larger than the width of the beam. So that's why we have this sort of saturation here in this part. And also you can see that depending on the number of antennas, and therefore the beamforming gain, the range so the performance versus distance can be of course increased, and this is just because we have a larger beamforming gain for the same transmit power. Okay, I have now a little time, it's a very little time. I want just to mention an application. So the application would be beam refinement and tracking. So first of all, what is beam alignment? Beam alignment is the problem that at millimeter waves, a mobile station may not even see that there is a millimeter waves base station, even if they are very close, if the beams are not aligned, simply because the link budget must be close, must be above a certain threshold, and typically you need at least one-sided and most of the time two-sided beamforming, so to have the combined beamforming gain of transmitter and receiver in order to close the link and bring the after beamforming signal to noise ratio above a threshold, for example 0 dB. If you can communicate a 0 dB with a capacity achieving code, you can communicate at 1 bit per second per hertz, 1 gigahertz of bandwidth, you have your 1 gigabit per second link right there. So basically bringing the signal to noise ratio from like -20 to -30 dB, 20 to 30 combined beamforming gain is the goal of this type of systems. The problem is how you do the alignment of the beams before, when you're working at -30 dB. When you're working at -30 dB, is the problem is very difficult. So there are, of course, schemes based on protocols, like, for example, beam scanning and feedback. So the base station scans some beams, the user listens, and then will transmit the index of its best beam, provided that this transmission in the reverse direction can be done at very low rate. And of course, we have a lot of results that indicates with simulations and measurements that at high frequencies, these channels are quite sparse in the angle delay domain. In general, in the angle Doppler delay domain, we have also developed generalized beam scanning schemes that for which both transmitter and receiver explore simultaneously several directions, a little bit in the vein of this projection matrix I was talking before, and then one can solve a compressed sensing type of problem that is completely non-coherent, just in power measurement, so it is robust to Doppler frequency offset. It's really like something that has to happen before communication. So even timing is a problem here, but it works well at so we can assume that after these beam alignment procedures that are mainly based on protocols, we have a situation where a user is assigned a beam, and this beam is one out of this perfect. It will never be exactly at the center of the beam. So there is some initial alignment error simply because these beams have some tolerances. So then we can use, for example, the radar information in order to do beam refinement. For example, in this case, we have looked at the problem of designing now this matrix U such that it is relatively pointy. So we use, in fact, the eigenvectors. We have NRF RF chains. So we take the NRF dominant eigenvectors of the covariance matrix of induced by say the line of sight propagation in a range of directions that around the broadside, so minus beta pi plus beta pi, where beta is a design parameter and typically is a bit larger than the resolution 1 over number of antennas of the array. So these sequences, these eigenvectors, are called the Slepian sequences and are well known in beamforming. They create a top. If you take NRF of those, provided NRF is less than beta times NA, those are unitary, mutually orthogonal vectors, and therefore they create a tall unitary matrix. Then we apply a phase shift, so a beam steering. So in order to look in the direction of the nominal angle, so it will look at this, it will be phi hat. So in this way, we can obtain a vector observation to extract angle information. And so this is, for example, these are radiation patterns of the first 1 to 3 Slepian sequences for the case of 64 antennas. And we can use simply good old music to get the angle of arrival from this vector information by simply collecting enough samples and constructing a sample covariance matrix. And of course, we can also use the maximum likelihood approaches before. Beamforming, this is 1 bit. So basically, this would be the threshold of SNR before beamforming for this number of antennas. I think this is 64 antennas, for which we can get our bit per second per hertz. And now you can see this dash curves corresponds to pointing errors of 0.5 degree, 1 degree, and 1.5 degree. And you see that if the pointing error is 1.5 degree in this case, well, we are very, very far from our target. And in fact, we are going to get here. So this is almost 10 dB is 10 dB of gap. Okay, but if we can do beam refinement, in fact, we will get in this case we will get this yellow curve here. So basically, we can recover in this case 5 dB. Of gap, which is quite good. And in the case where the initial error is 1 degree, we can recover like about 3 dB. Of course, if the initial error is very small, like 0.5 degree, well, there is nothing to recover. And in fact, we see that in the interesting region, basically, well, in this case, there is nothing to do. But that's an example of how this radar information would help for free and give you like a 5 dB gain with respect to the case where the beams are not refined. Another example is in beam tracking when there is motion. So when there is motion, of course, one can extract this radar information and this gives, repeated measurements. So we have a sequence, a time series of noisy measurements with the parameters, of course, are angle of arrival, the velocity, and range. Then we could put them into a tracker, and the tracker, well, it can be done using standard Bayesian statistical inference. For example, it can be according to a certain model. For example, if we make like a Gauss-Markov model, we would use a Kalman filter. If we make like something that is non-linear or discrete, and we consider like a hidden Markov model for the mobility, then we will use basically the forward recursion of a BCJR algorithm, which is the optimal predictor for hidden Markov models. But because because machine learning is inflation, and especially because this would be a quite ideal application of machine learning, because mobility models are complicated, and in general, we don't have a very good statistical description of mobility models. Even if when we have, it's still always an approximation of reality. So why not simply learning the models implicitly? And so in this case, one would use a recursive deep neural network. And in particular, we have considered bidirectional long short-term memory networks. And so what happens, for example, for even a relatively complicated mobility model where this is a simulation where the path loss is and the scattering is obtained by the simulator quadriga, and we have a trajectory that like a rectilinear trajectory, and then it becomes like a circle. Imagine a car moving along a way and then getting into a roundabout, which is typical in Berlin, by the way. There is a Grossesterne in the middle of the Tiergarten, which is the central park of Berlin, is a gigantic roundabout. So in this case, the network would learn these statistics and incorporate, basically learn the prediction model in order to basically do whatever your favorite particle filter or extended Kalman filter would do. So this is a simulation for that particular dynamics, where we have an oracle prediction, which is this blue that gives the perfect position and therefore the perfect pointing of the beam. The red one is what the recursive neural network gives, and the green one is a particle filter. So I don't want to make like a general statement here, because we are very far from this, but I would say that this type of inference, where the statistical models are actually pretty either complicated or also unknown or imprecise or partially known, this is an ideal, say, playground where learning implicitly the models directly from the data, using therefore, for example, supervised learning is can give, of course, very good performances. And in this case, it seems that this recursive neural network, which implicitly track the dynamics of a complicated dynamic process, seem to be the right structure to do this type of tracking. Okay, so we get to a conclusion where, what can I say? I think that it is pretty clear that this add-on feature of sensing can help communication. Of course, it may also be the other way around, that communication can help sensing. For example, we have just seen a very, very, very tiny example. If you already know that you are communicating with an object, you don't need to detect it. And if you already know that you're pointing a beam in that direction, the angle of arrival estimation cannot be more than the width of the beam. So you have already a pretty well a good idea of what the angle of arrival will be. So anyway, it seems that the major problem of sensing with digital modulated waveforms is the complexity of the receiver, simply because it has a wide band, and therefore we need either two collocated arrays and a transmitter and receiver, or full duplex processing. That's an ideal the receiver knows exactly what it was transmitted. So this means that one has very large blocks, provided that one can sample and memory and put in memory and process very large blocks of data. So the let's say frequency resolution, it can be very high because you have a long frame at your disposal. The delay resolution can be very high because you have a very large bandwidth. And of course, using these tricks of projecting a large array into a small dimensional RF chains, so beam space domain representation, and designing carefully these projecting matrices, one can also have a very good angle resolution and accuracy. So this is just a little bibliography to some of our recent works. Of course, there are a lot of more parallel works. It's a very alive field. That's why we are here. That's why there is this initiative. And I would like to thank you for your attention.
Okay, thanks, Giuseppe. And we have received lots of questions regarding your wonderful presentation. And I have collected some of them, and I'll ask the questioners to ask the question by themselves. So I think the first question is from Dr. Ahmad Nimr. So Ahmad, can you please unmute yourself? So he has a question about the OTFS.
Yes.
Ahmad? Hi, Ahmad. Can you hear us? Hello?
Yes, I hear you. Sorry.
Yeah.
Yes, so my question is about OTFS. So we heard a lot about OTFS, but if I look carefully at the signal processing part related to OTFS, so I see that the main advantage that is using 2D block, that means some signal spread over frequency and time. So what is really the specialty of OTFS? Why we cannot just simply use any 2D block instead of saying it is OTFS?
Right. So, of course, I probably have a partial view on this. I have always been very skeptical about OTFS. But then start working with, in particular, one of the PhD students, and we made some papers and read many papers from other groups. I have a little bit changed my mind. So from a communication viewpoint, of course, OTFS has one interesting feature is that somehow, if the channel is effectively sparse in the delay Doppler domain, so it is of the form that we have seen in this presentation, a sum of discrete multipath, each of which has a delay and a Doppler shift. It turns out that the channel estimation becomes very simple. Basically, you just send one symbol surrounded by many zeros in the Doppler delay domain. This symbol will be scattered into this the position of this multipath. Because there are zero all around after all the transform, it's easy to estimate those components. And now imagine, for example, a channel that has only two paths, which is pretty typical in millimeter waves. You have the line of sight and one reflection. Typically it's the ground reflection, but it could be like a wall or a bus or a metal plate, something. The rest you can neglect because it's going to be attenuated so much, right? In addition, when you have beamforming at both sides, many of the multipath disappears because it's simply filtered out by it. But now imagine this. So we have two paths, and there is a big difference in Doppler shifts. So this channel, if you see this in the time frequency domain as a transfer function, is a terrible channel. It's very frequency selective and very time selective. Our typical OFDM structure that puts the pilots in a line, in a sort of combo frequencies at some point will collapse. You have a time variation across a single block, okay? Because it's very fast. However, in the Doppler delay domain, these are 4 coefficients. Once you get 4 coefficients, you know the channel for, in principle, an unlimited amount of symbols. You can have huge blocks and still don't have to re-estimate the channel all the time. In fact, the size of the block depends on when these parameters change. Of course, if you have a mobile scenario, also the Doppler and the delay will change with time, but at a much lower pace than the channel transfer function when you see this as a time varying transfer function. So you can afford a very, very small pilot overhead. The only thing that limits the size of the blocks is complexity. And then we have also a paper where we have considered a message passing low complexity receiver, and then we have compared this for actual channel OFDM, and OFDM in this case, because the channel changes in a single frame, you have to spread out the symbols all around your block, and then you have to do MMSE time frequency interpolation. Now, when you take all this into account, it's so complicated to estimate the channel and interpolate it over time frequency for a rapidly varying channel, that at the end, even the OFDM receiver is not so simple anymore. And in fact, it turns out that that they are pretty comparable in terms of complexity. They are both linear in the block size. And when you look at the fact that one OFDM has one CP per symbol, while OTFS has one CP per block, you know, all these things put together, you see that in fact OTFS outperforms OFDM. The complexity is similar, but you have to be clever and use a low complexity message passing receiver with a soft output, and the overhead, the pilot overhead, is much less, and also the CP overhead. So overall included, I was like prevented against OTFS, but I have to say, just for a communication viewpoint, it can be convenient in the case where the channel is very sparse and the Doppler spread, the Doppler difference between the multipath is very large. In other cases, of course not. If you have a nice channel that is like a diffuse scattering and mobility is limited, absolutely not. I would never use OTFS. I would use OFDM because the channel estimation and the receiver are so much simpler in this case. You do like a block fading is constant over each block and everything works fine. And this is why we use, you know, after researching for years and years in preparation of 5G new waveforms, then people realize that the new waveforms are the old waveforms because we are still stuck with the cyclic prefix OFDM, which is great because it's really, in those conditions, it's almost unbeatable in terms of complexity and performances.
Okay, thank you, Professor Caire. And Ahmed, do you have any other comments, or I can?
Yes, actually, still regarding the comparison between OFDM and OTFS. So OFDM is somehow, if we look at OFDM, it's just sending one symbol and trying to estimate the channel from there. Yes, but OTFS actually is nothing but some encoding over a group of OFDM symbols. So the encoding there over time, or the precoding over time, is again DFT. But do we really need DFT? What, for instance, if we use another unitary matrix, like we are talking about complexity, for instance, using Hadamard matrix, which is less complex than DFT. So I think we could get again the same performance as OTFS.
Probably it's at the end you have to look at you know, performance versus complexity versus pilot overhead in the case of a time varying channel, and OTFS is an idea, is using FFTs. You can use Hadamard transforms and see what happens. Absolutely, why not?
Thank you very much.
As long as the comparison is well done and is really to find shortcuts, like you know, say, oh, let's assume that the frequency, the Doppler shifts are integer multiple of these. Oh, let's assume that the multipath, the delays are integer multiple of that. Of course, then everything is easy. Everything is low complexity. But no. You have to, one has to do the right thing, use the right models. And then, and also for the channel estimation, include because you don't know the channel, which means also, you know, how much pilot overhead you need to estimate the channel at a certain level of accuracy, such that your coherent receiver, whatever receiver you're going to use, gives the performance you want. And then you have the real comparison. And of course, there is no theorem that says that OTFS is optimal. I mean, it's the only thing I know is that for a linear time invariant channel, OFDM is near optimal, because this is a Shannon water filling, and this is comes directly from information theory. But for a time variant channel, a random variant channel, like a filling channel, there are so many models, and who knows.
Okay, thank you very much. Thank you, Ahmed. Thank you, Giuseppe. And another question also regarding OTFS. Please unmute yourself.
Yeah. Hi.
Yeah, please go ahead.
Yeah. So my question was related to the previous question. So I know that FMCW can offer some specific advantages in terms of sensing compared to OFDM, like full duplex or the limited ADC bandwidth. Does OTFS offer any advantage in terms of sensing? I'm asking because I also saw the results that Professor Caire presented, and basically the performance was almost the same or even slightly worse. And I have a second question regarding to the previous answer. Regarding the channel estimation part, there was a comparison with OFDM and interpolated channel estimates over the subcarriers. What if we compare with parametric channel estimation with OFDM? Does OTFS?
Well, okay, now there are several questions to which I don't have an answer, because they are very specific, and if they don't, you know, I don't know everything, of course. I only know what I know. I would say, related to your first question, in terms of sensing, OTFS and OFDM, I would say, I want to, you know, say it like a blunt statement. Any signal with the same duration and the same bandwidth that looks sufficiently random, so it looks like when you look at the time domain, it looks like random noise, because it's perfectly known at the receiver. In this case, you don't have to estimate anything. There are no, like, everything is pilot, so you know exactly what you send, right? Would have the same, roughly the same performances in terms of estimation. The fundamental point is, you know, think of this in terms of ambiguity function. If you have a wideband signal over a certain amount of time, more or less your ambiguity function, it looks like something extremely concentrated, where the concentration in frequency is the inverse of the duration in time. The concentration in time is the inverse of the bandwidth, and that's it. So this is this tells you that any digital modulation that is not like completely stupid, that is using all its dimensions, and those modulations like OFDM or TFS, they use essentially all the dimensions. With OFDM, you may argue that the cyclic prefix introduces some cyclostationarity, so it's not, there is an overhead there, so it's not really using all the dimensions. With OTFS, because of course at the price of a but you know, you do like filter bank OFDM without the cyclic prefix, and you would get exactly the same performances. I mean, exactly is not true. You will get essentially the same performances in terms of sensing. Now, the second question was, what about using a parametric channel estimation? Of course, I mean, if you use a parametric channel estimator, for FDM, you would have the same type of advantages, that if the channel depends on 4 parameters, even if as an impulse response or a transfer function changes very rapidly, but it still depends on 4 parameters. If you estimate, the problem is in which format it's easy to estimate those parameters, right? And at the end, you know, it seems that OTFS, because of the file structure that you can construct, gives a little bit easier way, because the way you plug the, you know, at the end you have to plug the pilot somewhere, You don't plug if you plug the pilot in the time frequency, you have a structure. If you plug the pilots in a Doppler delay, you have another structure. So but of course, you know, if the channel estimation is similar, it seems to me that for a channel that is sparse in the Doppler delay domain, it is somehow nice or somehow fits the sparsity of the channel to somehow work in the domain, but it may be wrong. I don't know.
Thank you very much.
Okay, thank you, Anastasius, and thank you, Giuseppe. And another question from Professor An Liu. So go ahead, please go ahead, Anne.
Hello, Professor Giuseppe. Haven't seen you for a long time.
How are you?
Yeah, I'm fine. I hope everything is fine with you.
Yes.
Yeah, okay. Anyway, my question is that as you have mentioned waveforms such as OFDM or OTF to realize radar sensing at the base station, then it seems that we need a full duplex base station, right? However, most works on joint communication and radar sensing has ignored current full duplex technology power enough to support accurate radar sensing. So can we continue to ignore this issue in the future work?
Well, I can only tell you that this is a problem that seems to, and everybody says, oh, assume we can receive and transmit at the same time. Because on one hand, communication is continuous. Well, yes, there are guard intervals, but they are not like you don't transmit pulses and then silence, pulses and silence. Then, if you have a chirp that shifts in frequency, what comes back is a different frequency of what was sent. You have two filters following the transmit and the receiver. But you can separate them by these two filters, and then you can sample, etc., etc. And that's why radar receivers can be all digital, even if you have an array, and they work very well. I mean, automotive radars work like this, and they have digital arrays, and they work. But the problem here is that with the wideband signal that is essentially continuous in time, because the communication waveform does not stay idle for time, it's the full duplex, or at least to have a co-located. So something may not be full duplex. You can also do full duplex with like two separate arrays. You can have your radar array as long as you have calibration. So somehow they look in the same direction, they have the same angular reference. You can have two different arrays and have them, separate, such that the signal that is re-injected, the crosstalk between transmitter and receiver, is not saturating the receiver front end. But it is definitely something that should be studied more closely. Maybe there are works that address specifically this problem, but I haven't seen them very. So it looks like a full duplex in a certain sense for radar is a done deal because the way the system is designed, but to use wideband digitally modulated signals is probably one of the major hurdles in practice.
Okay, I see. Thank you. And I have another question. Actually, it's related about the accuracy of radar sensing, because you have talked about using radar sensing to aid communication, right? And the basic idea is to first estimate the location of the mobile user using this radar sensing technology, and then we can obtain some information about the line of sight channel, and then we can use this to do beamforming or something like that, right? But my problem is that because the radar echo signal usually has lower SNR than the downlink signal or the uplink signal, right? Then is the radar sensing accuracy enough to add the estimation of the communication channel? Especially for this, millimeter wave and massive MIMO channel, they may have very large beam. If the prediction is not very accurate, then it may not help to add the communication, right?
Yeah, I mean, you can see, for example, just for simple example. In this beam refinement, now it's so messy that it's impossible to see, but let me erase this. In this beam refinement case, you can see very clearly that the refinement based on angle variable starts working. You know, for example, take this curve, this is with refinement and this is fixed. They start working here where there is a crossover. But in fact, you start being interested more or less in this region because more maybe we want this target of 1 bit per second per hertz. It's just, you know, it could be 1 bit, could be half a bit, but okay, this is more or less what we want. It could be more. If it is more, well, of course, if it's 2 bits, of course, the gain is larger. But this is to say, there is a region in which your estimation is so bad that is not helping in this case. Of course, this is a very preliminary result because you have also to take into account that you don't have just one estimation. This is a one-shot problem, right? But in fact, the angle does not change so fast. You have thousands of slots with roughly the same angle. So what about you put them into a denoiser? What about you put them into a tracker, into a Kalman filter, or something like that? So of course you are accumulating many measurements. And you know, if you have 1,000 measurements that you get right there, you have 30 dB gain. So when you have 30 dB gain, then your minus 30 becomes 0. So you're gonna operate in a, so it really depends on the range of variation. You know, these parameters typically change at a speed which is at a rate which is much lower than the rate of communication. Here, if you have a 1 gigahertz of bandwidth, you send so many frames. Before the angle has changed significantly, you have really thousands of blocks. So with a nice tracker, a nice denoiser, just just a Kalman filter would do miracles here. So what I'm saying is that I think that one has always to qualify the problem and define really well the conditions. So sometimes people get, you know, in love with one thing, but don't think, is this actually relevant for the system I want to consider? Is it the best I can do? This fantastic compressing algorithm, I want to apply it at all costs. But if you reverse the problem and you look at the problem first, maybe there are other things to do. And those, you know, loss in alternate ratio, yes, in one shot is absolutely very low. But when you integrate over say 100 blocks, you have a 20 dB gain right there, right? So.
Yeah, I see. Okay, thank you.
Okay, thank you, and thank you. We have a final question from Professor Jinhong Yuan. So, Professor Yuan, can you please unmute yourself?
Hi, can you hear me?
Yeah,
Yes.
I can hear you.
Okay, thank you. Hi, Giuseppe. Hi, everyone.
Hi.
Very impressive talk. It's really enjoy it. I just saw your detection performance on OFDM and OTFS, and quite similar. I think that's understandable. Just wondering, do you have any insight or result on the complexity issue on the detection for these two different signals?
Yeah. So I don't want to say something totally stupid here because, but I think that the overall and frequency, so delays stays inside the cyclic prefix of OFDM, and the Doppler shifts are significantly less than the inter-carrier spacing. And normally, I would say 99.9999% of the cases we are in those cases. Then the OFDM, even for this type of parameter estimation, is significantly simpler. And the reason is that when, for example, you have a Doppler shift, which is, I don't know, let's say 1000 hertz, okay, 1 kilohertz is a very large Doppler shift, but your spacing is 15 kilohertz or maybe more. It depends on which frequency. Maybe it's 150 kilohertz if you go a factor of 10. Basically the intercarrier interference is essentially negligible. Basically, you're going to have a very simplified, and if the delay stays inside the circuit prefix, at the end you end up with something that is essentially OFDM by the books. And when you have OFDM by the books, you have also much a simpler structure to deal with. In general, this is not true, because when you have intercarrier interference and intersymbol interference, then also the OFDM receiver has to consider the whole block. And then if you consider the whole block of n times n, you have like n subcarriers and n symbols in time, the complexity is pretty much the same. But these blocks, when you look at this, in other words, when you look at this linear model and say, oh, it's a linear model, it's simple. Yes. But with OFDM, most of the time, these linear models are diagonal matrices that multiplies your symbols, and these diagonal matrices have a nice Kronecker structure that you can exploit. While for OTFS, those are full matrices, and you have to really consider the whole block. So I would say that yes, OFDM gives lower complexity also for the parameter estimation case.
Yeah, I tend to agree with you. But on the other hand, if you're in the simple, in the carrier interference is very, very small, you probably rely on the time frequency domain estimation, and it is a small it might be difficult to detect the Doppler accurately. Does that make sense? Or for OTFS, you probably have the freedom to play with different domains, like you can play with the delay Doppler domain and the time frequency domain, or even time domain. So I think there might be some complexity issue may need to be considered. I think, yeah.
Yeah, so this was not very much our experience here. So it was a priori we couldn't predict that the performances in terms of estimation error for this, say, Doppler and delay would be so similar and would be almost indistinguishable with respect to the FM CW, and also would collapse on the camera bound essentially at the same signal to noise ratio. So it was kind of a priori kind of surprising, because when you look at the formula, you look at they are quite different. So it was a little bit, for me, it is a surprise that they perform so similarly. And by the way, those results are obtained for the OFDM case, are really obtained for realistic numbers, and therefore the Doppler shifts are fairly smaller than the intercarrier interference. So we have used, say, a receiver that assumes no intercarrier interference, although there is in the model. The model is not like, the model is exact, but the receiver is neglecting a lot of things. But what the receiver is neglecting is very, very small. So we are in these conditions. So it was a kind of strange, or strange, or maybe it's not strange. Maybe it's expected, but it certainly is not something that I would have said a priori. That all these fairly different signal formats were so similar at the end.
Yeah, I tend to agree. If you based on the time frequency domain to do signal processing, probably they achieve the similar band, because that is what you can do the best. I think that probably, or I just wondering, your detection probably is also in time frequency domain rather than delay Doppler domain. If you do delay Doppler domain, might be have some complexity reduction. I'm not quite sure. Just ask. Yeah.
The OTFS estimator work. I mean, the search So the likelihood function is a function of tau and nu. So the delay and Doppler. So the search is done by discretizing this domain and looking at the peaks of the likelihood function, and then doing a local search. So it's really in the Doppler delay. So in other words, these algorithms really consider the channel in parametric form and look at the parameters of the channel in the Doppler delay domain.
Okay, thank you.
Okay, thank you, Professor Yuan, and thank you, Giuseppe. I think that'll be all the questions, and we have so many questions and exciting discussions. So thank you for today's presentation, and I would like to sorry, Giuseppe, can you please stop sharing your screen? And
yes, sure.
Yeah.
Okay.
Yes. So I would like to. So this is a preview of our next seminar, which will be given by Professor Yunina Elda from Weizmann Institute of Science of Israel. So this will happen on June 16th. So we expected to see all of you to join us and to discuss the exciting topic of integrated sensing and communication together. And also we expect to see you in many other events that we're planning to organize within this ETI. Okay, so thank you very much for attending, and thanks a lot.